In this lecture, we're going to talk about different ways that we can use the partition function. So we introduced the partition function in the last lecture, and I said, trust me, this is going to be important. Now we're going to see why it's important. There'll be a couple of times during the lecture where I give you an example problem and then say, okay, pause the lecture, try this out, and then once you think you have a solution, come back and continue watching, and I'll give you the solution. Do actually take the time to work these. Working through these on your own before you see the solution is going to help you understand what's going on much better, and it'll also prepare you for the problem set. We're going to cover a couple of topics. We're going to start with what you can see on the screen now, thermal excitation. If we have some atom, what's the probability for it to be in an excited state? Then we'll look at how multiplicities of states change this. Okay, so if I have a degenerate state where there's, say, 3 or 4 states that have the same energy, how does that change the calculation? Then we'll use the partition function to calculate averages, and finally to calculate the fluctuations. So things like the standard deviation, variance of the distribution. So in the first 2 lectures, we've developed a lot of formalism for how statistical mechanics should work. In this lecture, we'll really start using it to do some interesting physics. The first thing we want to look at is thermal excitation of atoms. So we'll consider the hydrogen atom, which you should know from quantum mechanics. The hydrogen atom has a spectrum where the energy in a given principal quantum number n looks like this. So minus 13.6 eV times 1 over n squared. Okay, this has the same form as the Bohr model of the atom, which obviously is not right. We're going to ignore things like spin-orbit coupling. Actually, we're going to ignore the existence of spin at all for the time being. It turns out it won't make a big impact on the calculations that we're doing. So for now, we're just going to ignore it. We're going to pretend a hydrogen atom is a spinless proton and a spinless electron bound together by the Coulomb force, and that's it. That turns out to be a good approximation for the kinds of calculations we're doing now. So one question that we can ask, based on what we talked about in the last lecture, is the ratio of probabilities to be in different states. So the 1s state is the lowest energy state, that's the ground state, and the 2s is the first excited state. This is the lowest energy state above the ground state. So we're just going to ask, what's the probability that we have an atom in the excited state compared to the probability that it's in the ground state? And we know from last time that this is just the ratio of the Boltzmann factors. We could actually write out the probability completely because we talked about the partition function last time, but that would just put a 1 over z in the top and the bottom, and those would cancel, get us back to the result we started with. And now I'm just going to collapse this down to a single exponential, so it's e to the minus beta times this 10.2 eV, which is the difference in energy between the ground and the first excited state, between the 1s and the 2s. In other words, this is the excitation energy for an atom. So the energy to give it a single excitation. Now, if we look at room temperature, so 300 Kelvin, we can calculate kT. Okay, just plug in the value for Boltzmann's constant and the temperature in Kelvin. This gives us an energy, right? Because Boltzmann's constant is essentially our conversion factor from temperature to energy. And then I'm going to convert again just to go from joules to EV, since I wrote this in what I will call the correct form in terms of the half the Rydberg energy, which is 13.6 eV. So this comes out to be 2.59 times 10 to the minus 2 eV. And I've taken this number and boiled it down into a nice rule of thumb that you can use, which is at room temperature, so about 300 Kelvin, maybe you keep your room at 295 Kelvin. That's not a big change, right? That's a 1 or 2% change. So at room temperature, KT is about 1 over 40 EV. Okay, 1 over 40 would be 2.5. It's 2.59 again. That's why it's called a rule of thumb. This is good to 5% for sure. Okay, there's an error here that's a couple percent. Again, if your room is at 295 instead of 300, that's another couple percent. So this is good to 5% at least. So at room temperature or normal temperatures that you're accustomed to, KT is 1 over 40 EV. That's a good way to sort of get quick estimates for things. Obviously on the homework, if I give you something where I've given you 3 significant figures, the answer should be to 3 significant figures. But knowing this off the top of your head may let you sort of check, well, if you ask me a question about this, I expect based on this rule of thumb, the answer should look like so. Okay, so now at 300 Kelvin, we know KT, so we know beta is 1 over KT. The ratio of these probabilities is just e to the minus beta times e. Now we can calculate this out, and here's where you might use the rule of thumb. Say, yeah, beta is about 40, and the energy, beta is about 40 per EV, and the energy is 10 EV, so it's going to be like e to the minus 400. Do the actual calculation, you get e to the minus 394. Okay, that's close. That's your sort of, you can use the rule of thumb to check where you expect to be. You always trust that your calculator has multiplied correctly the numbers you asked it to multiply. Maybe you didn't ask it to multiply the right ones accidentally. Okay, and we can convert this into a power of 10. This is 10 to the minus 171. So for scale, the estimates for the numbers of the total number of particles, protons or electrons, neutrons, in the universe, but dominantly protons and electrons, the number of particles in the universe is somewhere in the vicinity of 10 to the 100. Okay. So this means even if every single particle in the universe was a hydrogen atom, if they're all at 300 Kelvin, there's still a vanishingly small probability that we would find any of those 10 to 100 atoms in its first excited state. So at room temperature, we're never going to find a thermally excited hydrogen atom. Might have been excited through some other process, through a spark, through a laser, this sort of thing, but we're not going to find one that's just been thermally excited. Okay, how about at 6,000 Kelvin? No longer room temperature, even if you like to keep it warm in the house. Okay, this is like the temperature on the surface of the sun. So pause the video, work through the calculation, be sure that you understand the mechanics of it, and then we'll come back and see the solution. Okay, have your solution. Let's see what we've got here. So the same mechanics apply. The ratio of the probabilities is the ratio of the Boltzmann factors. We can reduce that down to a single exponential. Now our beta instead is 20 times higher. So this is our beta, and the excitation energy is the same. Just do the division, it's e to the minus 19.7 or 2.8 times 10 to the minus 9. So now, for every billion atoms, 2 or 3 of them are going to be in the excited state. That's quite a departure. And that really comes from the fact that we're using exponentials here. So the numbers change very dramatically when you change the exponent. Okay, maybe this is something you sort of know intuitively or would have said offhand, but now you're sort of seeing it in physical terms. At room temperature, even if every atom in the universe was at room temperature, we're incredibly unlikely to find one in its excited state. In the surface of the sun, okay, 3 out of every billion, that doesn't sound like a lot, but again, Avogadro's number is 10 to the 23, so even in a gram of hydrogen on the sun, you've got something like, well, what that ends up being 2 times 10 to the 13, okay, 20 trillion out of every gram. Okay, there's a lot of grams in the sun. An alternate way to do this, rather than just literally plugging it into the same formula, this may be a bit gives you a bit more of an intuitive feel for this, is to say T prime, our new temperature, is 20 times our original temperature. So that means our new beta prime, is our old beta divided by 20, which is to say the exponent has the same, so this exponent up here, right? Once we reduce down, the excitation energy is the same. So the E part of the Boltzmann factor is the same, but the beta has dropped by 20. So this ratio will just look like the same answer, but with the exponent divided by 20. Plug this into a calculator and confirm, yes, this gives you the same answer. Okay. So when your temperature goes up by a factor of 20, this ratio goes, the exponent in the ratio goes down by a factor of 20. Okay. So in the sun, we're going to have a lot of excited state hydrogen, though still, it's only 3 out of every billion. The vast majority of the hydrogen, even on the surface of the sun, is still in its ground state. The hydrogen example I simplified in a couple of ways that I mentioned, right? I'm assuming that neither of the proton nor the electron has spin. And I said that's a good approximation. We'll talk in the future about why that's a good approximation, but the short answer is just that the spin excitations are so much lower energy than the excitations to different ends that they end up being irrelevant. On the other hand, there's another approximation I made which is not good, which is I assumed there were only 2 states in the hydrogen atom. It's actually a lot more than 2 states in the hydrogen atom. So what we want to look at now is multiplicity of states, and I've drawn a couple more of the states in the hydrogen atom in here. So before I said there's a 1s state and a 2s state. You know from quantum mechanics that there's also the 2p state. And the 2p level, in fact, is 3 states, right? So p refers to angular momentum L equals 1, and within that p level you have m sub L equals +1, 0, and -1. So we won't worry about energy splittings between those, right? We can assume there's no magnetic field on, in which case there isn't a splitting between them. Or there's a small magnetic field and the splitting energy is small. There's actually going to be, in a real hydrogen atom, a spin orbit coupling that's much bigger than that. Even that is small enough that we're still going to ignore it. So we're just looking at this gross structure, ground state versus excited state. But the fact that the excited state has a multiplicity is important. And you can see why here. Right? If we're calculating the partition function, we need to add up the Boltzmann factors for every state. If we ignore the 2p level, this partition function would just be e to the minus beta energy of the 1s plus e to the minus beta of the energy of the 2s. And what I was trying to do there is underline this 4. So if we ignore the 2p, that 4 isn't there. Now I put that 4 there rather than writing out explicitly e to the minus beta times minus 3.4 eV for the 2s, e to the minus beta times negative 3.4 eV for the first 2p, right? For the second, for the third, you get the point. I could have written this, strictly speaking, as a sum of Boltzmann factors for every individual state and just identify each state, but these all have the same energy. So I'm just going to get a 4 out front, right? And so this is what we mean by the multiplicity of a state. If I'm only identifying states by energy, then degenerate states will have a multiplicity. And now I just want to connect this up to some things we've already discussed, right? We could just stop the story there. Hey, don't forget to multiply by multiplicity. That's fine. That's what this formula is telling you here, right? When I calculate the partition function, in fact, I can save time if I have degenerate states, right? So if my SI only identify the energy, then I can sum over the multiplicity times the Boltzmann factor. So be a little careful here. If in your state description you have described everything about the state, right? If state S3 is the 2p m sub L equals plus 1 state, well, yes, this is still technically true, but the multiplicity is going to be 1, right? If you completely describe the states so that all of your multiplicities are 1, this reduces to our old formula, just the sum of the Boltzmann factors. But if you've said, yeah, S1 is the n equals 1 state, S2 is the n equals 2 state, now I've ignored this substructure. I've ignored this degeneracy, so I need to put the multiplicity of 4 out front. Now I just want to mess with this equation a bit, right? We talked about how important multiplicity is for an entire system. Let's put everything in the exponent, just so that everything's on the same footing, the multiplicity and the energy. Okay, and we can do that, right? This thing goes into the exponent by taking its log. So e to the log multiplicity is the same as the multiplicity. When we bring the log into the exponent, I'd also like to divide it by beta, right? So not only do I want it up in the exponent, I want it to be of the form e to the minus beta times a bunch of stuff. Well, dividing by beta is the same as multiplying by kt, so this becomes e to the minus beta times the energy that was already there. And actually, we don't just divide by beta, we divide by minus beta. We want the minus beta out front. So this is going to be minus kt times the logarithm of the multiplicity of that state. And just a notational thing, writing out exponentiation like so is going to come in very handy, right? We're frequently worried about what's going on in the exponent of e to some power. And if what's going on up there gets complicated, trying to write it in this form where you've got this e and then the exponent gets a little smaller, well, if you're trying to squeeze a bunch of interesting stuff in there, it just makes it neater when you've got a lot going on to say exponential of this stuff. And just as when I write log, you should understand I always mean the natural logarithm unless I put an explicit base on it. When I say exp, the exponential, I implicitly mean e to the power, not 10 or 2 or anything else. If we want to do one of those, okay, we're going to have to just write it out. But we're going to do e to some power so often that having this as a shorthand, or not really shorthand, but a neater way of writing is helpful. Okay, I go on for entirely too long about things, I think. That's fine. So now we've got these things on even footing, right? We've got e to the minus beta times the energy of the state minus kt times the log of the multiplicity. And I've already underlined something in orange here. K times the log of the multiplicity was something we talked about in the very first lecture, in the review lecture. For a system, that's the entropy. Now, does it make sense to define the entropy for a state? Well, yes or no, but you're not going to go out and measure the entropy of a single state necessarily, but we can still call k times the log of the multiplicity the entropy. So this gives us a nice form that really connects you back to thermodynamics, right? Instead of having the partition function just be all of these Boltzmann factors purely in terms of energy, if your subsystem is more complicated, you can think of this in terms of e to the minus beta times e minus ts. And if you look back to your thermodynamics, this quantity is the free energy. Now we want to use this to calculate something a little more exciting. So in this astrophysics example, we're going to look at measuring the temperature of an interstellar gas. So it turns out you can use probability ratios to calculate the temperature of an interstellar gas. And the way you do this is by looking at absorption lines from the gas. So we've got some gas that's between a star and us, and the light from the star is essentially a flat black body radiation. Now we'll talk about, actually, the star has absorption lines in it as well, but let's just assume for now it's a flat black body spectrum. Okay, so there's light at every frequency, and if this gas is a particular molecule, let's say it's cyanogen, carbon bonded to nitrogen, or carbene, carbon bonded to hydrogen, there will be specific absorption lines that are sort of a signature of that molecule. So in other words, some of this light will not make it through. We see that as a dark stripe in a spectrum, and from that we know the composition of the interstellar gas. But now looking even more in detail at exactly what frequencies are missing, we can learn not just about what molecule it is, but about the temperature of the molecules. Okay. So I've drawn here this sort of probably intimidating looking level structure. Sorry guys, and I'm an atomic and molecular physicist, so this is like my day-to-day. Let me explain this a bit. Okay, so what's going on here? Let's just take one molecule in particular. Let's take cyanogen. Okay. Now, molecules are like atoms in the sense that their electrons can be excited to different energy states. Okay, so we just talked about hydrogen. There's the n equals 1. There's the n equals 2. We didn't talk about it, but you know from quantum mechanics there's n equals 3, 4, 5, all the way up. Okay. Now within those there's substructure, like we talked about the 2s and the 2p. Those are two different angular momentum states, but with the same energy. In molecules, again, you can do the similar thing of transitioning the electron from, it's not exactly as simple as a principal number state, but let's pretend it is. Okay. Pretend this is the n equals 1, or the lowest energy molecular potential, and this is the n equals 2, the first excited molecular potential. So you'll see I've drawn this little wiggly bit here. This is just saying there's a break in the axis. In other words, I'm showing you these levels having a little spacing, and these levels having the same spacing, and then a little more spacing between these levels. But in fact, the gap between the sort of, again, in quotes, n equals 1 and n equals 2 states, that gap is dramatically bigger. Okay, so when we look at some absorption line due to this structure, there's going to be sort of one feature, one broad feature, which would be an absorption in the violet, right? But now if you get a better and better diffraction grading to resolve down the exact wavelengths, what you'll see is what used to look like one single structure splits into several. Okay. And that's because of this energy difference. So within the ground potential, within the ground molecular potential, we also have the possibility that the molecule is rotating. Okay, so the molecular potential is sort of defined in the molecule's axis, right? Just fix the carbon and the nitrogen here and here, and there's some potential energy between them. If they're rotating, if they're oriented like this, that sort of doesn't matter to the molecular potential. So R equals 0 and R equals 1 refers to either the molecule is not rotating, or it has one unit of rotation. Okay, so just as for the hydrogen atom you have L equals 0 or L equals 1, but nothing in between, a molecule can have 0 units of rotational angular momentum, 1 unit, 2 units, and so forth. And it's quantized in the same size as angular momentum of electrons, namely h bar, Planck's constant divided by 2 pi. So if the molecule is not rotating, it has a certain energy. If it's got 1 unit of rotation, it's at a slightly higher energy, right? That makes sense. If it's spinning, it's got more energy. And similar to the p level in the hydrogen atom, you have 1, 2, 3 different rotational sublevels, right? So this could be rotating like this, it could be rotating like this, it could be rotating like this. Okay. In the excited molecular potential, there's a similar structure. It could be not rotating, in which case there's just one state. It can be rotating with 1 unit of angular momentum and have 3 sublevels. It could be rotating with 2 units, in which case there's 5 sublevels. This is like your D state in the hydrogen atom, the 3D sublevel. Okay. Now, I've drawn all of this because you can get different transitions between these different states. If I'm in the R equals 0, there's only one transition I can make. I can absorb light that's exactly the right frequency to take me to R equals 1, or I called it R prime equals 1, 1 unit of rotation in the excited potential. If I'm in R equals 1 in the ground potential, so I've got 1 unit of rotation in the ground potential, I can either go to R prime equals 2, in which case there's 3 transitions, or I can go to R equals 0, in which case there's just 1 transition. Okay. So different multiplicities, different things that are allowed. If I shine this starlight through a bunch of cyanogen, carbon bonded to nitrogen, and then I disperse the spectrum, what I'll see is mostly just a flat band of light. I'll see 3 little notches taken out of it. The one in the middle corresponds to R equals 0, R prime equals 1. The one at longer wavelength, which is to say lower energy, corresponds to this R equals 1 going to R prime equals 0. And the one at higher energy corresponds to going from R equals 1 up to R prime equals 2. Okay, so that's the spectrum that we're looking at. And we want to use this spectrum to tell the temperature of the interstellar gas. How can we do that? We're going to look at the relative strengths of these absorptions. Okay, so I know the strength of this line and the strength of this line will be proportional to the population of molecules in R equals 1, right? They have to start in this rotationally excited state to be able to make either this transition or this transition. Whereas this will be proportional to the population in the R equals 0, in the actual rotational ground state of the molecule. Brief break for me to fix a mistake in my notes. So now, based on the ratios of the strengths of these lines, we can figure out the ratio of these probabilities, right? So the probability that I'm in this first excited rotational level, in this R equals 1, compared to the probability that I'm in the rotational ground state, is 1/3, not 1/5. Had a typo in there. It's not a typo if you write it. It's a righto? I don't think so. Anyway, it's correct now. It's 1/3. Okay. Now, the other things that we need to know are, what is the energy difference between R equals 0 and R equals 1? And I've written this for both cyanogen and carbene. For cyanogen, it's 113 gigahertz. You can measure it in a lab on the Earth, no problem. For carbene, similarly, we can measure it. It's 534 gigahertz. So we've been looking at cyanogen. So based on this ratio, you should be able to tell me what temperature the gas is at. Okay, let me scroll up here. You should be able to tell me what temperature the gas is at. And then once you know the temperature, you can tell me what's the ratio of the probability for being in R equals 1 to R equals 0 for carbene. Okay, so again, this is going to be a problem for you. Go ahead, pause the video, do the calculation, and then come back and keep playing, and we'll see the solution. All right, ready? So let's see the solution here. Oh, okay. I'm going to start by setting the rotational ground state, the R equals 0, energy equal to 0. It's just going to make it easier to calculate the partition function. And with that energy scale, the energy of the first rotational excited state is just H times delta. Remember last time we went through this and showed you can change the 0 point of energy however you want, and it doesn't change the answers to physical questions. We're going to ask a physical question. Great. So the probability for being in the rotational ground state is the partition function, or rather 1 over the partition function, times the Boltzmann factor. If we set the energy equal to 0, the Boltzmann factor is 1. Makes life easier. The probability to be in R equals 1, 3 times 1 over the partition function times e to the minus beta h delta. Okay, so the ratio of these, again, we could have gone straight to the ratio the partition function factors cancel out. I just wanted to be a little explicit since this was going to be 1 in the denominator here. Okay, so all we have left is the 3 from the multiplicity of the rotational equals 1 state. Let me scroll back up here. Remember, r equals 1 has a multiplicity of 3. So we're 3 times as likely to be in that as you might have guessed because we have 3 different states to fall into. And they will each one of them will absorb light in the same fashion. Okay, they can all absorb the light, so good. E to the minus beta h delta Cn comes down, and that ratio of probabilities is equal to 1/3. Divide by 3, take the log, bring the minus sign over, we get that the exponent, beta h delta Cn, is equal to log 9. And now we're just going to rewrite this, okay? So if beta is 1 over kt, bring the t to the other side, bring the log down. What do you have? T equals h delta Cn over k, Boltzmann's constant, times the log of 9. And now all we're going to do is stick numbers in for these. Here's Planck's constant. Delta is 113 gigahertz. Remember, gigahertz is 10 to the 9 per second, so 1.13 times 10 to the 11 per second. Boltzmann's constant, log of 9. Plug that all in, and you'll get a temperature of 2.4 Kelvin. Okay, pretty cold, 2.4 Kelvin. Second part, take this temperature and now use it to calculate the ratio of the probability to be in the r equals 1 versus the probability to be in the r equals 0. Okay, so we can do that. Same result as above. It's going to be 3 e to the minus beta h delta, except now it's delta ch. It's the carbene rotational splitting. Okay. Now, I have written this in what I'm going to call a lazy way, which is to say, there's a lot of things with units and exponents, and oh man, this looks like a lot of work to me. I'm going to instead say, hey, wait, the beta and the h are the same as before, right? We're at the same temperature, so same beta. Planck's constant is a constant, it's not going anywhere. So I just need to change from delta ch to, from delta Cn, which is where I was at before, to delta ch. So if I take my old result, which was that beta h delta Cn equals log 9, then I just have to multiply that by delta ch over delta Cn to cancel off the delta Cn. See? So I multiply by that ratio times log 9. The ratio, 534 gigahertz over 113 gigahertz. It's about 5. It's actually a little smaller than 5. Okay, it's 4.73. Put this all together, we've got the 3 times exponential of minus log of 9 is 1/9 raised to this power, this 4.73. Do the math out, 9.2 times 10 to the minus 5. Okay. So it turns out that the probability to be in the first rotational excited state for carbene is much smaller than the probability to be in the first excited rotational state of cyanogen. Okay. How does that help us out? Well, when we actually look at the spectrum, we can see clear peaks, or rather clear dips, right? Dark spots in the spectrum, because it's an absorption spectrum. You see these dark spots in the spectrum that correspond to the different rotational levels of cyanogen, whereas when we look at carbene, we will not see those 3 levels. Or if we have a really good instrument, we will just barely detect the 3 absorption features and be able to look at those ratios to compare, do we get the same temperature in that calculation, right? If we look at these 2 peaks in carbene and their ratio is 9 times 10 to the minus 5, that's what makes it hard to measure, right? You've got to be able to measure things to a part in 10,000. Not impossible. So you can measure that and say, hey, if I get that number, that tells me the temperature should be 2.4 Kelvin. My measurement in cyanogen also tells me it should be 2.4 Kelvin, so those match. Now the last thing I want to say is this number, 2.4 Kelvin, that might make you think about something, which is the cosmic microwave background. Now, if that phrase doesn't mean anything to you, don't worry about that, because we're going to talk about the cosmic microwave background later. But for those of you who have seen a little bit of cosmology, you may have heard that the entire universe is filled with a background of radiation. It's basically the echo of the Big Bang. Okay, so right after the Big Bang, the universe is full of electrons and protons and photons, and they're all sort of bumping into each other. They're all in thermal equilibrium. And so we have, right after the Big Bang, whatever, the temperature is extraordinarily high. As the universe cools down, at some point it gets cold enough that electrons and protons can come together to make hydrogen and not just get torn apart again by collisions with a bunch of other high energy things, right? So this is a question of temperature, and there'll be a question like this on your problem set. Once the temperature gets low enough, electrons and protons can stick together to become hydrogen. And when that happens, hydrogen doesn't have sort of broad absorption features. It has very narrow lines in its spectrum. So when you produce hydrogen instead of free electrons and protons, suddenly the universe becomes transparent. And so the photons, which were in thermal equilibrium with everything else, suddenly can't change their frequency anymore. So they're stuck in this black body thermal radiation state. And then as the universe expands, that black body spectrum is preserved. It just gets to lower and lower temperature because the frequencies are shifted. Again, if all of this sounds like crazy talk to you, don't worry. We'll talk about this much more in a couple of weeks. But for those of you who've seen it before, the microwave background radiation shows a temperature of 2.7 Kelvin. Now this isn't quite 2.7 because I used some old data. Newer data does come out with, and I should say, newer data plus a more careful analysis of what this ratio actually means gives you a temperature of 2.7 Kelvin. So in fact, the interstellar gas is roughly in thermal equilibrium with the cosmic microwave background. And this is something we can learn by looking at the ratios of these absorption lines. And just to finally wrap this all up, let me show you where I got this data. There you go. So this is the R equals 1 to R prime equals 2 absorption line. This is the R equals 0 to R prime equals 1 absorption line. And all that's happened from here to here is they've run a low pass filter over the data, so it's cleaner, easier to analyze. Look at these two peaks, you can measure it, ratio of 1/3. Okay. Now, like I said, you have to analyze a little more carefully if you want to get right on 2.7, but we've already gotten quite close to discovering the microwave background. These measurements were actually taken before the microwave background was discovered, and we're just sort of a curiosity. Why is this gas happen to be right at this temperature? So if you wanted to read more about that, this is the paper, the short wavelength spectrum of the microwave background. So this is in fact a way to measure the microwave background sort of very far into the microwaves, where at least in 1972, you could not design good microwave detectors. Today, I think you'd be able to do that. So after I recorded the last lecture, I realized, I'd been careful to try to explain the basics of probability in case you hadn't seen these sorts of things before, and that hit me. You have to take quantum before you can take this course. So you definitely should have seen probabilities in quantum. Similarly, you should have seen averages, though in quantum you may have called them expectation values. The calculations are the same. Okay? And certainly you've seen averages in other places in your life, right? So just to say it formally, the average, and we're going to use this over bar because it's what Schroeder uses for averages. So x with an over bar is the average of x, and we get that by adding up every possible value for x times the probability that we'll get that value. Okay. So the example we looked at last time, this canonical distribution, right? That's where the Boltzmann factors come in. If we want to know the average of x, some physical quantity related to our system, again, it's the sum of the x values for all of our states times the probabilities of those states. The probability is 1 over the partition function, 1 over z, times the Boltzmann factor, and then there's our x. Okay. So this is sort of as far as we can go if I don't know what this quantity x is. But one of the things that we'll very often want to know about is the energy in the system, right? So in the canonical distribution, canonical ensemble, we're taking our subsystem is thermally connected to a reservoir. The reservoir has a fixed temperature. We're thermally connected to that reservoir, so our subsystem is at the same temperature. And now we want to know, say, what's the energy in the subsystem? So the expectation value, or the average for the energy, is going to just look like this same formula, but with E of SI plugged in, right? So we just put E of SI, that's our X, that's what we want the average of. And now we notice something that makes the partition function extremely valuable. There's an E to the SI here, there's an E to the SI up here. And in an exponential, right, the derivative of the exponential function is still the exponential function. So we can write this thing as the derivative with respect to beta of e to the minus beta times the energy. Right? Check that for yourself if it's not obvious. The e is going to pop out, and then you'll still have the exponential. But this beta, or dd beta, doesn't depend on I, so we can pull that out front, right? So what's out front? Oh, I should have said it's a derivative with a minus sign, right? Because when you take the derivative with respect to beta, you'll get minus e. We don't want minus e, we want e. So just drop a minus sign out front. So this becomes minus 1 over the partition function times the derivative with respect to beta of this sum. But that sum is exactly the partition function. So what we've found is that the average value of the energy is minus 1 over the partition function times the derivative with respect to beta of the partition function. And then just a slightly more clever way to write that, is to say it's minus the derivative with respect to beta of log z, right? If I take the derivative of the log, just use the chain rule. You get a 1 over z, and you get the derivative of the z. So this is equivalent. And in this form, you will use this very often. So this is definitely something to commit to memory. The average value of the energy for the system is just minus the derivative with respect to beta, the log of the partition function. For the last topic, I want to just talk about fluctuations a bit. This is statistical mechanics, so the average value, as we've argued earlier, will tell you a lot, right? The sort of the center value of the distribution is very narrow around that center value. I'm thinking particularly in the first lecture where we talked about the multiplicity of some large collection of oscillators in an Einstein solid, but this will be a general thing, that the fluctuations around the center value will be small, but they won't be zero. And so we'd still like to know something about these fluctuations. To talk about fluctuations, we're thinking about a distribution of energies in our subsystem now, right? First, we found the average. That's going to be sort of the center value of the distribution. But now we'd like to know how wide is that distribution of energies. So to define that, we're going to look at the variance, okay? Sigma squared. It's written sigma squared. If you take the square root and just get sigma, that's what we call the standard deviation. And again, this should be familiar to you from quantum mechanics, because when you develop the Heisenberg uncertainty relation, that's in terms of variances. But as a reminder, or in case you didn't cover that quite as in depth, the variance is the average value or the expectation value of the squared deviation from the mean. Okay, so that's a lot to unpack. All we're saying is for each I, take the value of x, take its difference to the average, and then square that. Okay, so more or less what we're looking at is the distance from the average value to this particular x. So you picture some data that's scattered around, right? I go up to get to this x, there's that distance squared. I go down to get to this x from the average, there's that distance squared. So we're looking at the squared deviations, and then we're weighting that sum by the probability for each x. Okay, so how likely am I to get a particular x times the square of its distance from the average. So this is giving you some measure of the spread in the data. Now, that's a good definition for it. It may not be the most convenient way to calculate things, though. So the next thing I want to do is derive a sort of nicer formula for how you can calculate the variance. And all we're going to do is square this out, right? So we get xi squared minus twice xi times x bar plus x bar squared. The probability is still sitting here. Now just separate this out into three sums, one for each term. Okay. So we've got the sum on I of xi squared times the probability of xi. We've got an x bar, right, the average value of x, that doesn't depend on I, so we can pull that out of the sum, along with the minus 2, doesn't depend on I, so that pulls out of the sum. So we just have the sum of xi times the probability of xi. And for the last term, x bar squared doesn't depend on I at all, so that whole thing pulls out, and we just have the sum of the probabilities left. And now we're just going to use some properties and definitions, right? Sum of xi squared times the probability of xi, well, we set up above, right, the sum of anything times its probability gives us the average. Okay. Probability of xi is exactly the same as probability of xi squared, right? You know, one determines the other. So this is just x squared bar. Okay. We've got the average value of x squared rather than the average value of x. Here we do have the average value of x. So this 2x bar times the second x bar minus 2x bar squared. And lastly, we know that the sum of the probabilities has to equal 1. Right? The chance that something is picked is 1. So x bar squared, these guys, there's some canceling, and we end up with this very nice result, which is that the variance in some variable x is given by the average of x squared minus the average of x squared. Gotta be careful about how you say that, how you think about it, but we're taking x squared and finding its average value, and we're subtracting the square of the average value of x. Now, we also talked about variance actually in the first lecture in the situation where we said, what's the multiplicity of this Einstein solid when we have a particular split between QA and QB? Remember this? It's sort of two Einstein solids stuck together. And we asked, what's the multiplicity of the state when we have QA equals to Q over 2, right? Put half the excitations in one side of the solid. And what we found after a bit of effort is that the distribution looked like a Gaussian, right? This sort of bell-shaped curve. X bar or X average is up here in the exponent. That's the peak of the bell curve. And then we had this 1 over 2 sigma squared in the exponent. And sigma gives us the width of the distribution. Just a normalization constant out front, which we talked about also in the first lecture. So sigma, the standard deviation, tells us about the width of the distribution. Sigma squared, which is the variance, is this sort of nicely calculable thing. That's a lot of generalities. Let's talk about a specific case we care about. What case will we care about? The energy. Okay, so again, we've got our system in thermal contact with a temperature, with a heat bath or a temperature reservoir, right? So the temperature will be the same as the reservoir, but the energy may fluctuate. And so we want to know, how much can it fluctuate? We've got a value for sigma squared as E squared bar minus E bar squared. We already got E bar up here, so we just need to get E squared bar. And by we, I mean you. So pause this, see if you can derive a formula for E squared bar in terms of Z and beta. Remember the process we went through up here, right? See if you can use a similar process to find a formula for E squared bar only in terms of, I said Z, didn't I? Only in terms of Z and beta. Okay, do you have your solution? Good, let's see what we've got. So if I write E squared bar, just using the definition of the average, I've got a 1 over Z out front, sum on I of energy of state I squared, because that's what we want to average now is the energy squared, times the Boltzmann factor, and just going to use the same trick we did before, right? Taking the derivative with respect to beta drops down minus E. If we want 2 E's, just drop minus E twice. The minus signs even cancel, so we don't have to keep track of that. So this thing just looks like the second derivative with respect to beta of e to the minus beta e to the minus beta energy, let's say. And just as before, the derivative with respect to beta doesn't depend on I, so it pulls out of the sum. So we've got 1 over Z times the derivative, the second derivative now with respect to beta of the sum on the Boltzmann factors, which again we know is the partition function. So we now have sort of very clean expressions for both E squared bar and E bar. And in the problem set, you're going to put these together to calculate something much more physical than these sort of, oh, what's the fluctuation in the energy? It turns out there's a very physical quantity that relates to fluctuations, and you're going to calculate that on the problem set.